Thank you for joining my lecture on age, aging, and the proteome. So age is the major driver for dementia, but also other age-related diseases. But aging as a phenomenon, as captured by a person's biological age, may be a more important determinant of the disease. Now, a person's biological age may differ from his or her calendar age, and that can be estimated quite profoundly by omics profiling. So the current estimators of biological age are most often organ specific, but there's also a lot of literature out there looking at DNA methylation in blood as an estimate of the turnover of aging in an individual. Now, beyond DNA methylation, that really monitors quite well the amount of exposures and additions to the DNA that have occurred as a result of your lifestyle and all your exposures. There's also increasing interest in the role of the proteome. And the reason for that is that loss of cellular protein homeostasis is one of the key features of aging. And organ aging have been recently shown to be also visible as a phenomena in the blood when measured across a large number of individuals. So our mission was to set out to construct a biological age clock in the general population that predicts age-related disorders. And of course, our major aging disease that we were thinking of was dementia. But we studied a large range of other age-related disorders, from cardiovascular to bone diseases, and also cancer. So what we have done is construct, first of all, a proteomic age clock that we have published now in Nature Medicine, that received in the scientific community quite some interest. There was a research briefing in the journal, but there's also a comment on our work in Nature itself. And if you're interested, please look at these papers. So our basic work was done in UK Biobank and the China Kaduri Biobank. These are two studies that were conducted quite in parallel. If you compare the age distributions of the two studies, then the China Kaduri Biobank has a little bit more spread in the ages studied, starting before the age of 30 and continues after the age of 70. Well, if you can include older people in your study, you also get older people that die. And that's what you see at the age of death. The age of death is a little bit, but not dramatically higher in the China Kaduri Biobank. So we were interested not only in a clock for aging, but also in its association to diseases. And we studied that particularly in the UK Biobank. And basically what we did in the UK Biobank, look at the range of diseases, both in prevalent patients. So these were already ill at the time that they were included in the biobank, as well as in incident patients that really developed the disease during follow-up. Now, briefly, the design, what we did is we took the UK Biobank and split that in a training set for machine learning. We used gradient boosting for that, and a testing set, which is just to verify how well things work. That was 30% of the sample. We used Olink Explore, which have a little bit less than 3,000 proteins that were successfully determined in UK Biobank. And in the training set, what we did is a 5-fold cross-validation, and we used the Baruta feature selection to come up with a final model for biological aging. So what is basically we're doing is quite simple. We take age, time that is based on your calendar age, and start constructing a predicted age based on the proteomic data. Now, we have the testing data set to validate findings in, but you would like to have an external validation, and for that we use the China Kadoorie Biobank. But in the process of publishing our data, we also added kindly the FinRisk data in there. So, how well is the correlation between the age, your calendar age, and your proteomic age? That is high in the UK Biobank. In the training set of about 1,300 people, you get a high 0.9. However, if you look at the CKB, who had 600 people, where we did the same trick, so there you get a very high correlation of about 0.89. So that really works well. So what do we do next? Well, what we first of all did is just replicating the findings what we had in UK Biobank, both in China Kadoorie Biobank and in the extra study FinRisk. But what we also did is we didn't rely on one program for the machine learning, which was gradient boosting, what was our first preferred system. But we also rerun the analysis using an elastic net analysis and a neural network. And in all cases, actually, we got the same similar findings and the same similar associations to the disease. So that was enormously helpful and enormously encouraging. And the next step was to define those people that we thought of that they were successful aging. And successful aging, that we really simply define that given your chronological age, your proteomic age clock really says that your age is lower than your calendar age. Now, the opposite, if you go faster in your aging process, the accelerated aging, you are above your predicted age based on your birthday. And in that case, we think that you are probably going at a faster rate than others in the same calendar age. So, first of all, the clock itself, how well does it work? Well, if you compare the predicted age range between females and males, they're very similar. But what you also see that there is quite a big difference between people who are in the upper and lower end of the distribution. It may be 12 years or more that you differ in biological age. If you are a lucky person who ages slower than predicted based on your birthday or faster. We didn't see a lot of differences between people of different race, or in the case of the China Kadoorie Biobank, you see that the distribution is quite similar of people over the different ethnic groups in the population in China. So, what we did next is ask ourselves, how does this phenomenon of accelerated or successful aging correlate to risk factors of the disease? And we studied a lot of risk factors that we thought are indicators of aging. The first two, cystatin C and creatinine, are typical kidney aging. And if you work in geriatrics, there's a lot of people with kidney problems that are coming up in the clinic, and it's one of the most established problems in aging. If you work in more the laboratory, then you know that telomere length and IGF-1 signaling is an important entity in animals, and both of them in the full study in the UK Biobank really are strongly correlated to this measure of accelerated or successful aging. You also see emerging C-reactive CRP, C-reactive protein, and that is of course one of the phenomena that we all know, the inflammation aspect of aging. Inflammation is an important feature. And what we find also, the liver is popping up. Now, in terms of risk factors, clinically measured, you can just ask a person, how's your health? How well can you walk? And do you think you face age more than of others of the same age? All of these are associated to this outcome. Other important measurements clinically of aging is being tired, being frail, also associated, but also sleep problems, your blood pressure, your reaction time, which is more brain related, arterial stiffness as a readout of vascular problems, BMI, bone mass density, and as of course hand grip are all associated to these measurements. Now, this is the full sample of 40,000 people we characterized in the UK Biobank, but we also did a reality check. Is this really now a causal relationship, or is this because the disease is already present when we constructed this clock? And if we look at the people who are disease-free, you see that most of these associations are really maintained. The one that if you start with a disease-free cohort, which is about half of the cohort that we started out with, what is dropping out is some liver measurements, but also albumin. And albumin, we all know, is a protein that reflects your health status very much. So if you exclude those others, what really drops out in this reality check is being tired, not a good sign, and really the sleep problems, more than 10 hours a day, are dropping out. So what about the next step? And the next step that we are interested in is, how does this accelerated age measurement also predict the mortality and disease risk in the UK Biobank? It does, and I think what you see here depicted is all-cause mortality. You see type 2 diabetes, ischemic heart disease, and stroke, and you see that there's a major difference between the groups indicated. If you look at the blue line, that is the top 10% that accelerated most fastly, so these are the unlucky people. The orange line are those people who are in the middle, so these are the 45% to 55%, or just smack in the middle. And the green one is the lucky ones who are the successful ages, so the top 10% of the distribution of this delta that has a lucky outcome. Now, if you look at the cumulative incidence, then you see that most of the risk of mortality, accelerated age clock, is really in this top 10%. And you see also that this holds true for the risk of type 2 diabetes, ischemic heart disease, and stroke. You also see lung diseases popping up, COPD, but also the liver disease and kidney disease, as predicted from the previous slide, are popping up as diseases associated to this. So, do we see the same in the China Kadoogie Biobank? Well, yes, we do, but the study is smaller, and it's not that the study is smaller, I should say, the number of participants characterized is smaller, and therefore we can only look at very common phenomena. That is death, so mortality really shows the same pattern as we just shown for the UK Biobank. Stroke definitely is an important cause of death in the Asian population, and China in particularly. Ischemic stroke in particular, and ischemic heart disease also shows the same pattern. Now, as a neuroscience person, of course, we are also very much interested in Alzheimer's disease and Parkinson's disease as the major problems from a neurological perspective that we have data on. And again, all-cause dementia, again, we see that there is a steep increase in those who show accelerated aging. And that's even for persons who you measure at baseline in a age range of 60 to 65 years. There's a probability that they develop dementia in the coming 12 years, or the coming decade, is about 20%. That's incredibly high. So most of it is explained, of course, by Alzheimer's disease, and also for Parkinson's disease, the second most common neurodegenerative disorder in the population. We see a similar effect. What else do we see? Well, if we look at a phenomenon that occurs in aging, is usually that there is no one single disease, but people suffer from multiple diseases. That's also what we see in our present data set. So if we just count really by age that you were included in the study, so 40 to 50 years or after 30 years in figure 3, what we see that the average score of your aging, if you have 4 diseases, is significantly higher than if you have only one disease. So that's already true very much at the age of 40 to 50. So what we are measuring here, we think, is an estimate of proteomic aging or biological aging that really you see increasing with the number of pathology that you have through relatively early in life already to be seen between the age of 40 and 50. So that is true for overall, but also for the self-rated. So if you ask somebody whether you think you are really at poor health compared to others or excellent health, you see still this association emerging. Now, just summing up with some new data, because one of the problems we anticipated and was brought up in our discussions is what about your sex? So I think if you work in epidemiology or clinic, then we all know that there's major differences in aging patterns between men and women. And one of the points that was brought up by Najaf Amin, already when we try to do this using metabolomics instead of proteomics, we have to look between the sexes and study the females and males separately. And this is quite new work done by Tifel in our group, Xiao Chow. And what he basically did is rerun all the analysis using a different estimate for males and females. So in both sexes, the R-square is extremely high. It definitely doesn't go down. But what we also see that there is a core set of proteins that determine aging, biological aging in men and women. And that's what we expect, right? Because we know that the men, for some diseases, take cardiovascular disease, they develop this disease probably a decade earlier than women who are for a long time protected for particularly high, a range of these risk factors as long as they haven't passed the menopause yet, and then they start catching up with the men. So about 1/3 of the proteins do differ being selected between men and women. And that's an interesting phenomenon, and that is what we exercised further. So is there a big difference between men and women if you just compare the risk of the disease? And this is measured on the scale of the relative risk. So what this shows that if you look in women and measure the risk by standard deviation of this healthy aging score or unhealthy aging score, you see that there is a 1.5 times increased risk by a change of SD on the risk of Alzheimer's disease. So what we see again, and that is very similar to the overall finding, that we find the most strong associations to this outcome to Alzheimer's disease. And that is true in the in the overall analysis, putting men and women together. You see that there's also some difference occurring, but it's more a matter of, for the top diseases associated, is just a matter of ordering. Although all-cause mortality, I think that's much stronger in the men compared to the women. Now, the major change that we see is more a bit of a shift, and that is more easy to see here. So in the women, of course, we do see in the UK Biobank difference in types. Dementia, ischemic stroke is strong, but ischemic heart disease is significant, but not as significant as we see in the men. The differences are quite much stronger for heart disease in the men as compared to the women, and that's exactly as you would have expected, because that's a phenomenon that we have seen and we know should happen also. The major shift that we saw is that in the overall analysis, actually our proteomic aging score didn't correlate very well with cancers. And that becomes different if you do this stratification for sex. So in women, breast cancer, of course, that will not pop up in the men, very likely. However, if you look in the men, we see a much broader range of cancers coming up, which are quite known to be age-related also. Esophagus cancer is an important one in that, but also prostate cancer is an important one of an age-related cancer. So the major step forward, we do see marginal differences between men and women for cardiovascular disease. The most important jump forward that we see is with cancers. So summing up, take-home messages. So we see an accelerated proteomic age signature that really stratifies the population for morbidity and mortality across ethnically really different populations. We see that again and again, Alzheimer's disease is the winner, not so much in the number of patients, but how big the gap between is it to the most rapidly aging people and the people that show a little bit more successful aging. And we see that aging profiles do differ between men and women. A large part is the same, that's what we also expect, but there's nuances that appear really more towards the cancer prediction. And apart from an aging clock, really this accelerated aging also gives us an impression of people who are developing multimorbidity in the near future. That brings me to the acknowledgement to the people who did the hard work. Austin Argentieri, of course, did the fantastic work that is, most of the work that is published now in the Nature Medicine paper. Xihao Xiao really has worked hard on developing this aging concept clock, starting with metabolomics, but now shifting also to the proteome, and Najaf Amin, who is in my group, the senior person that steers us to the major questions like, is it really true that men and women age in the same way? Also a big thanks to Laura Winchester and Leo from Oxford University's Department of Psychiatry, and for my colleagues from the China Kaduri Biobank, Derek Bennett, Robert Clark, and Zhengmin Chen. And with that, thank you to the sponsors.